So I'm Bart Remes. I'm project manager of the Micro Air Vehicle Lab in the University of Delft. And we develop micro air vehicles. And one of them will show up quickly on the big screen. Yeah? Okay, perfect. Thank you. So we do research on very small flying devices. In 2013, I predicted that in 5 years, everybody will have a small drone in their pocket, like they have smartphones in their pocket now. So I still have a few years to make this happen. So we work very hard to have this happening. And how do we do this? We, first of all, design our own very small unmanned aerial vehicles, like very small fixed wings, but also very small multi-rotor wings. And we believe this kind of systems will be like, you have a little bit of talks about Internet of Things, like everything's connected, and this will be your 3D connectivity. So normally you stay fixed on one pole or you only walk on a surface, and this will be your third dimension in this Internet of Things. We don't make only drones for ourselves, but we do everything open source. So for instance, we also make a very small autopilot, which is powerful enough to make a very small system completely autonomous. So if you see this one here, this is a complete autonomous system with a very small autopilot on top, which is this one. And this autopilot is freely available on the internet. All the schemes are available. The only thing is you need to attach a GPS and then you can fly your waypoints outside. Why do you want to use this kind of autopilots or drones? For instance, a fire or a policeman has caught by a problem, and before they already arrive at the problem, they already can take a look with aerial images where the problem is, where the fire is. With infrared camera, you can detect the fire spot, and with this, you can already prepare while going on to the incident area. But it's not only for police or fire brigades, it's also for you. So people are now investigating in how to make these systems even smaller so that they can be wearables. So for instance, Intel is investing a lot of money in Nixie, which is a very small drone, which is used like your watch. And if you want to make a selfie of you, you don't make a selfie anymore, but you make a droney. You throw the droney in the air, it takes a picture of you, come back, and you wear it again as a watch. We at the Micro Vehicle Lab try to make these systems more intelligent. So I already told you about a small autopilot, but we also integrate a camera on top of this. Why do you want a camera? For instance, if you are flying these systems inside the city, with the autopilot you can tell them to go from waypoint A to waypoint B. But suddenly there is a crane standing in between, and the autopilot doesn't know that. So the system has to be intelligent enough to scan his surroundings and see this obstacle and plan around it. So what I will demonstrate here is a very small flying device with such a camera. It's a stereo vision camera, so it's the same as your two eyes. If you put your finger in front of you and you close one eye and then the other, you see the finger jump from left to right. And with this system, that's also what the camera does, you can see distance from the object. So there's a small light in front of the camera. When it sees an object, the small red light will go on, and when it doesn't see an object, it stays out. And what I will demonstrate is I will fly this system, first manually, then I will set it to automatic mode, and I will walk towards it, and it will back off because it thinks I'm an object which it has to fly away from. So now I'm controlling it myself. I will put it to automatic modus. And whenever it sees me, it backs off. And when it doesn't see me, it tries to come back. So this kind of systems make drones more intelligent and make sure that this kind of systems can be in your pocket And you don't have to think anymore about controlling a drone, but you just throw the system in the air, and it's intelligent enough to do its own stuff. Here you can see a little video of what kind of software is on board of this stereo vision system. So it has to keep a constant distance from the wall, but not only a constant distance, it also has to try to stay on the same spot. If the camera doesn't contract your drone, it's like a tennis ball. If you push a tennis ball, it keeps on rolling. But with this stereo camera system, it contracts the push and tries to stay at the same spot with the optical flow information from the small camera. And this video will show you a complete autonomous navigation system. It's indoor, so we have a fake GPS indoor where we take off, and it has to go from point 1 to point B. But in between point 1 and point 2, there's an obstacle. I'm standing there. So it has to replan its route around the obstacle, and then go as quickly as possible again to the original route. And now when he arrives at point B, he has to land again. So this is completely autonomous, no pilot in control, fully autonomous, decided by the drone itself how to navigate from A to B. So you can imagine that I'm not standing there, but there's a building standing there, and if drones want to fly inside cities, they have to solve these kind of problems. We not only focus on very small flying devices, with multiple rotors, but we also focus on flapping devices. This is one of the examples. This is, for instance, a Delphi. It flaps with its wings. It's inspired by nature. And why do we focus on these very lightweight, very difficult devices? Because we're a research group, and we always try to take the most difficult roads. But also, if we can solve it for these very lightweight devices, we can use this knowledge and put it on the bigger drones, the drones used by Amazon in the future to deliver goods from 1 to B. And these sensors will help to improve these Amazon drones to be more intelligent and do not bump into the buildings anymore. Also with this Delphi, there's more research going on, like how does this aerodynamically work and what's really going on. Insects can already fly with flapping wings for millions of years. And we only understand since 10 years how aerodynamically this is working. 10 years ago, we had formulas that calculated that bees could not fly. So that was very interesting. Now we finally understand how this kind of system can fly. We have a very small system with a lot of components. So you have battery, motor, actuator, motor controllers, and even a camera that transmits images to the ground to get interesting information. It's working by flapping its wings. So here you can see a slow motion video of what's going on there. And you see it's two pair of wings which flaps together and create a small vortex on the leading edge of the wing. And because of this vortex, the Delphi is sucked into the air. And that's also how insects are doing it. And that's why we can understand now finally how insects are flying. We try to also simulate this and measure this in wind tunnels. And then you get this kind of interesting pictures where you see the vortices going on and where the aerodynamics visualization of this kind of behavior is shown. In the wind tunnel, this is data coming from a wind tunnel. In the wind tunnel, we cannot see on millimeter level yet because the cameras are not accurate enough. So we also simulate it. And here you can see simulation in the computer. And now we can really see the leading edge vortex. So on the top wing, the red, and now the blue. And now again the red. On the front of the wing, you can see a small tornado where the Delphi is being sucked into the air. We also put on this Delphi the small stereo vision camera. And to make it more intelligent, to make it fly completely autonomous into a building. And this is actually what the stereo camera sees. So you have a left camera and a right camera. And from both images, you get a dipped image. And the closer the object is, the more red the image will be. And then the autopilot knows he has to avoid the obstacle. Here you can see a video of the Delphi flying completely autonomously in a room. And what you will see is we are only controlling the height, and all the rest is done completely autonomously by the autopilot. And you have to notice what will happen in the end. So you see that the Delphi starts following the walls, because that's the best route to not bump into any obstacle. The nice thing is that we can prove it in a very clean room, where not too many obstacles are. And this is actually what the camera is seeing. So now blue is good, no obstacle in the way. And when it's coming closer to an obstacle, it's getting more and more red. So the autopilot needs to start avoiding the obstacle. And for this, it can go on for, when the battery is empty. But it cannot only do this in a very clean room, but also in a random room. So we picked one of our laboratories, start flying the Delphi, and it also starts navigating completely autonomously in this random room. Because it's boring, we speed it up a little bit. That's the nice thing about autonomy. When it's getting boring, you did a good job. And to demonstrate you, Delphi is really flying not only on videos. I have one of them here. And this one I will control myself, but then you have an idea how this kind of stuff is working. So it's flapping with its wings, and because of that you can fly very slow. And you have to see I don't have to do much. It's a very stable platform. This one doesn't have the stereo camera, so it will not avoid the obstacles. And if we fly a little bit faster, you can see that it's tilting like a bird, more in forward flight. And then if I want to fly slow again, you can let it hover. These kind of platforms are very interesting for indoor navigation, because with some of these multi-rotor systems, if you come close to an object, it will suck itself to the object. But with these flapping devices, you can hit an obstacle and keep on flying. It doesn't have any problems with that. We also made a very small one. This is called the Delphi Micro. And it's 10 centimeter. And it has also a very small camera on its nose. And you see the live stream of these camera images to the ground station. And this one weighs 3.07 grams, so it's a little bit of a few sand grains. And this one was just a tech demonstration, so it can only fly for 1 minute. What are we doing else to make drones fly in cities and to make it a part of your daily life? We also make a combination of multi-rotor systems and fixed wings. A fixed wing is very efficient and can fly for a very long time, but it cannot take off everywhere, so you cannot use it in a city. A multi-rotor, you can take off everywhere, but you cannot fly very long, because it has to carry its all weight by the propellers. So we make hybrid UVs, and what you see here is a hybrid UV, which take off vertically, and then transition to normal horizontal flight like a flying wing. So this kind of systems would be perfect for in cities. You take off, you start flying above all the obstacles, and you start flying as a normal airplane in a very long flight time. You can be an internet hub for people, or you can deliver goods from house 1 to house 2. But there are other things which are interesting in cities. To make this kind of platforms more stable, we have to do a lot of research. And we use an open source autopilot for that, and we use a toy for this. This is a Pirate Bebop, which is just a toy you can buy. We put our own open source software on this kind of toys. All the students that come in our lab get a toy like this, and they have to prove their new technology on this toy. And when they showed it on this toy, they can get a real dangerous drones and then do their research further. And with this kind of toys, for instance, you have to see very good that we can do very aggressive maneuvers. For instance, here we will do a flip. So we go up and do a fully automatic flip. And why do we want to do this flip? Because if you want to fly in cities, there's a lot of gusts, and you have to fly very agile. And to fly very agile, you have to be very controllable. And that's what we try to prove with this kind of technology. And what we do also is we put the drones into the wind tunnel, and we simulate the windy environment like inside a city. So what you see here is a drone is flying completely autonomously into the wind tunnel and out to the wind tunnel. And what you see, it has to adapt its behavior when it flies into the wind tunnel and come out to the wind again. And what normal drones do is if you go into the wind, you will blow away to the back, and if you come out to the wind again, you will shoot to the front. And what our controller does is keep the path very clean, and that's what you need to fly in the streets of a city where the gust is coming from all sides and you don't want to be blown away by the wind. And we go even further. So in very gusty environments where the wind is like very high frequently gusty, we try to improve things with putting small sensors in the front and make the control even faster than what we already did, so that we can hopefully also fly in very almost stormy weather inside cities. All this research is done in the university, but we are also trying to bring this knowledge into society. And for this, we started a company together with the university where we try to take all this knowledge and put it in society, and the end goal is to bring the human completely out of the loop. With this kind of systems, you just want to gather information, you want to do something in 3D, and you don't have to think about it anymore. You just press the button, and the drone is intelligent enough to do it completely autonomous. Thank you for your attention, and if you have any questions, don't hesitate to ask them.
Thank you very much, Bart.